Hi guys. Today's lesson we're going to be moving on with quadratics. We're going to be moving on to some quadratic models. So pretty much the idea behind quadratic modeling is pretty much we're putting this equation y equals ax squared plus bx plus c, this quadratic equation or this quadratic function. And we're putting it into practical sort of contexts. So just remember, guys, that our quadratic equations have a highest power of 2. So this x squared gives away that it's a quadratic. So it's really important to pick up on that because in the HSC, etc., they're just going to throw equations like this at you, and you have to recognize that it's quadratic and that it's going to make some sort of happy or sad face parabola when they're graphed. Okay, so let's give this question a try. This question is a typical quadratic model sort of question. So the context is we're dealing with the area of a rectangular garden where the length is x meters. So we've got a couple of variables here. We've got that the area of this garden is varying. So there's different areas of all these different sorts of gardens. And also the length is varying. So x is our length. So as we vary the length of our garden bed, it changes the area of this garden. So what we're doing here, well, pretty much question A is to draw a graph of this function here, this quadratic. We know this is a quadratic because the highest power of x is 2, so this x squared gives it away. We can also see that this is a negative x squared. So I immediately think to myself it's going to be an example of a negative quadratic where it's a sad face. So let's draw the graph of this function. The idea is when you're graphing any sort of line or especially non-linear lines, ones that are curvy, you want to be using a table of values. So it just makes it so much easier because it tells you exactly what points this line is on, and so you can see exactly where your line is. So remember, make your x values nice and simple. I actually, in this sort of situation, when your x is dealing with lengths can only be positive. So here they start at 0 and they only go all the way to 6. So you probably didn't have to go all the way to 6, but it's a good idea too. It can, the more you do, the better. So in this context, you didn't have to worry about any negative values of x because length is always positive. Okay, so when we substitute our values of x into the equation, we get our values for a. So it's just typical substitution. So quickly showing that. So for the first one, when our x is 0, we've got 6 times 0, take away 0 squared, and that is going to be equal to 0. So that's how we get a 0 down there as well. And then if we're going to do it for x equals 1, we'll get equal 6 times 1, take away 1 squared, and that will equal 5. And then that's how we get our 5 right there. So pretty standard sort of stuff. You would have been doing this a bit last lesson. So when you finish that, you should get all these values. And when we graph these, you can see this is our points right here. And we can see that we get this sort of parabola. So there's our 7 points. Okay, so and that allows us to graph this. Now notice that they've only done this, they've only shown the graph in the positive sections for both A and X, so both your X and Y axis. And the reason is because the area of a garden is always just going to be positive. You're always only going to be dealing with these positive numbers here. Okay, so next question. Use the graph to estimate the area of a garden when the length of the garden is 4.5 meters. Now you need to remember what variable represents our length. That is definitely our x value. So we think to ourselves, we want our x to be 4.5. So if we look at our graph, 4.5 in between 4 and 5 right here. So I'll get the pen. So right here, there's our 4.5. We go up to our curve And then from our curve, we can see the estimate for the area. So it is going to be about 7 meters squared. Now, you can also, instead of just using the graph, you can also use your equation to estimate the area. So we know that our x is 4.5. If we substitute in our 4.5 into our equation, we get a better estimate than our 7. So putting in our 4.5 into this will get us 6.75. So it wasn't quite 7, but it was quite close. So yeah, you can use the graph or you can do it algebraically. The algebraic method is definitely more accurate. It's actually 100% accurate. Okay, so moving on, the next question. What is the maximum area of the garden? This is a question that I see all the time. They're talking about maximum or minimum areas. So this is where you have to look at your curve and look at your areas and think to yourself, where does the curve hit its maximum area? So looking at your curve, the maximum point along this curve is going to be right at the tip. This point here, when your length is 3, that gives you the maximum area. And if we estimate across, it's going to be something like a 9. So what is the maximum area of this garden? Most likely it's going to be 9. You can check that by substituting in your 3 into your equation. So if we go 6 times 3 minus 3 squared, that definitely does get us an area of 9 meters squared. So the maximum area you can have for this garden bed is 9 meters squared. And you would want to make sure your length is 3 meters. Okay, so moving on. The last question, what is the length of what is the garden's length in order to have maximum area? Well, it's pretty much just asking when it has this maximum area, what was the length? It was just this 3. So when x equals 3 is your final answer there. So hopefully this sort of question makes a bit of sense. Let's move on to something slightly different. So we're dealing with some stopping distances here. So when cars are pretty much stopping very quickly, the distance that the car travels when you come to a stop, when you suddenly realize that you have to brake, is found using this equation here, where you've got a few variables here. You've got a few different letters. You've got D is the stopping distance in meters, so that's what we're trying to find. That D, that's our distance, how far the car goes before it stops. Then you've got V, so V is the velocity, so obviously the faster you're going, the longer your stopping distance is going to be, so that is definitely a variable. And then you've also, and make sure that your speed is in kilometers per hour. Really important that you're following this unit. If I give you a speed in meters per second, you would have to convert it to kilometers per hour. And then you've also got T, which is your time reaction, so how long it takes you to react to something, and that is definitely in seconds. If I gave you that your reaction time was in minutes, you would have to convert it to seconds. But obviously, reaction time, you're going to be in a bad way if your reaction time is more than a minute. Okay, so we use this formula. Now, the reason this is an example of a non-linear relationship is, well, a quadratic, is because the highest power of this variable v is 2. So we've got v squared. Instead of x squared, it's now v squared. Okay, so the way to deal with this equation is to pretty much just find the different variables, so v and t really, and then put them into this formula. So here we've got our velocity is 60 kilometers per hour, which matches our units. So therefore, this is pretty much saying our v is equal to 60. And then we have our reaction time of 0.8 seconds. Now that is also in seconds, which is perfect. So our t equals 0.8. Which you can pretty much just plug straight into this formula. When you do this, you end up getting that your stopping distance is roughly about 35 meters. So pretty simple question there. The questions on this in the HSC can get a little bit trickier, but it's just using these sorts of concepts. So it shouldn't be too much trouble. Good luck with the questions. Bye.